Well, hello and welcome, everybody, to this inaugural lecture of Eloise Marais, Professor of Atmospheric Chemistry and Air Quality at UCL. It's my great pleasure to welcome you to this talk. Eloise told me I should keep it really short because Danielle Jacobs, her PhD supervisor, will actually do the proper introduction. So it reminds me to ask, first of all, if anybody wants to object to photos being taken, could you?
Yes, you are okay to email job.web@ucl.ac.uk if you don't want to have your photos taken off, but otherwise,
yeah, thank you. And then secondly, if there is a fire alarm, please, there's an exit there and an exit at the back. Leave the building through the entrance you came through, and then make your way through this little archway northwards towards the front of the print room cafe. I hope everybody knows roughly where that is. Otherwise, just follow the masses as they walk there. And finally, yeah, there is a drinks reception after this talk, which is in the cafe area you've all walked through on your way here. And that's basically me done. So I hand over to Danielle. And yeah, thank you very much for coming. Welcome.
Okay, good evening, ladies and gentlemen. And my name is Daniel Jacob. I'm a professor of atmospheric chemistry and environmental engineering at Harvard. I've been at Harvard, embarrassingly, for 39 years. But that gave me the wonderful opportunity to have Eloise as a student. So it was all really worth it. I'm told I have 5 to 10 minutes. So I'm going to stay. First of all, I figured I should introduce the field to you and tell you about how atmospheric chemistry is very, very interesting. So atmospheric chemists try to understand the factors that control the composition of the atmosphere and the implication for climate and for life on Earth. It's a very important fundamental problem as part of understanding the Earth system. It's also a problem with tremendous societal implications that you read in the news all the time. For example, wildfire plumes in the US, leading to very high aerosol concentrations. We're seeing that those fires, which are going to turn out to be a tremendous air quality problem. More generally, urban air quality, which decreases our life expectancy on the average as citizens of the Earth by 1.8 years. Remarkable when you consider that cancer reduced our life expectancy by 3 years, smoking-related diseases, 2.1 years, air pollution, 1.8 years. It's very much the silent killer. And then it goes on, deposition to ecosystem, deposition of mercury, of nitrogen, deposition of acids are all associated with atmospheric chemistry, the depletion of ozone in the stratosphere, the Antarctic ozone hole, and then the 800-pound gorilla of climate change. And climate change is initiated by changes in atmospheric composition. So atmospheric chemists have a responsibility to lead the charge towards better understanding of climate change. So we have all these wonderful problems to work on, and they involve all kinds of scales, from sub-kilometer to global. And they involve hundreds of gases and particles that interact chemically with each other and are coupled with transport, again, on all scales. So we try to observe a system. We observe a system with surface networks of air quality monitoring station or research sites, for example, the site operated by Eloise on the roof of the building at UCL. We use aircraft in commercial operation or aircraft as research laboratories. We use increasingly satellites. And all of this makes for an extraordinary array of information that we then need to process. And the way we process that information is through mathematical models. And so those mathematical models will describe the emission, the transport, the chemistry, the deposition of pollutants, And all of this, again, in a coupled manner between all the different species and on all scales. And this is deliciously complicated. Wrote in a book about it, but it's it's extremely okay. It's extremely complicated. Atmospheric chemists are a power behind. Well, I wouldn't say a power behind the increase in computing resources, but they're definitely a gobbler of any computing resources that will come their way. It's considered that atmospheric chemistry is a major computational challenge. Okay, at the same time, atmospheric chemistry is full of fascinating zero-order problems, things that we just don't understand at all. You know, we don't understand how many gases are oxidized in the atmosphere. We don't understand what's being emitted from lightning strokes. Until Eloise started to work on it with Connor, we didn't really understand how much was emitted from rocket launches. And maybe Eloise will tell us about this. The point is that there's a lot of problems that make for a very fertile opportunities for addressing simple questions where we just don't have the answers. Okay, so that's it for I hope I've convinced you that atmospheric chemistry is very, very exciting. I certainly excited myself telling you about it. Now I'm going to talk about Eloise. So, boy, you're really very lucky to have hired Eloise. I wish I could have hired her at Harvard, but didn't work out. So Eloise was trained as a chemist at the University of Natal and at Rhodes University. And she showed up on my doorstep at Harvard to do the PhD. And she wasn't sure what she wanted to do, but it had to be about Africa. Yeah. Because if you don't know that Eloise is from South Africa, don't worry about it. She'll tell you about it for 5 minutes. Okay, anyway, so Africa is very much a dark continent, as we all know, but it's very much a dark continent when it comes to observations of atmospheric chemistry. And so we started to work with satellite observations that were very new at the time, and did some interesting work on emissions of hydrocarbons from vegetation in Africa. But this is where I recognize that Eloise was somebody special, because she took this and then she said, okay, well, I want to understand better what those emissions are going to do. And we had some observations from a campaign in the US that tried to link those emissions to aerosols, but we didn't really know how to do it. And so Eloise developed a brand new chemical mechanism, the first explicit mechanism showing how emitted gases will produce aerosols, and this was a stellar accomplishment. That code is still in the major models that are used for atmospheric chemistry. And then I'm not sure how it came about, but she became interested in the upper troposphere and started to be interested in the emissions from lightning and trying to use satellite observations in a clever way. And it was, again, an indication that she was ready to move from project to project, following anything that she found that it was interesting. She was not scared of anything and ready for the challenge of using different tools to apply to different problems. Now, eventually, she was released from Harvard. And one thing I recognize in my best students is that they do their best work after they leave Harvard. And that certainly was the case for Eloise, because since she left Harvard, she's been doing this remarkable array of things, looking at ammonia emissions in the UK, looking at PM 2.5 in Africa, looking at emissions from rocket launches, looking at all kinds of different things. I mean, Eloise is really kind of a Renaissance person in atmospheric chemistry. And I had the pleasure today to sit into a meeting of her group, and we're getting presentation of different group members, working on all kinds of different problems. It was really pretty incredible. So with Eloise, you have somebody who's really able to move from project to project to project, very useful for defining atmospheric chemistry at UCL and putting you on the map. You definitely have somebody who will be able to move from problem to problem as the new problems develop. Now, Eloise has by now a remarkable record of publications, of funding, of honors, of leadership. And I should mention that she is now the co-model scientist for GeoSchem, which is considered the premier model of atmospheric chemistry used by hundreds of research groups around the world. And so she is now charged with keeping all those groups happy. So good luck. And with this, I probably used my time. So without further, I will welcome Eloise and looking forward to your talk. And congratulations to UCL for having appointed Eloise as a professor. You have made a better choice. You're so lucky.
Oh, that's incredibly kind, Danielle. And I think something that maybe you're forgetting, and I owe a lot of gratitude to you for where I am in terms of my career, is that I arrived on your doorstep with zero coding experience, not even simple Excel coding, and he took a risk in giving me this opportunity to do a PhD that was entirely coding heavy, and it was liberating. It moved me away from a lab environment where I was useless. I broke instruments. I had liquid nitrogen explode onto me once. My poor South African Rhodes University master supervisor, I think I broke her budget because I would keep breaking her UV cells. And I was just impatient. Things didn't happen fast enough. And I produced green blobs while other people in the lab produced these beautiful sparkling green crystals. So, and also importantly, I didn't get the opportunity at high school. I was denied access to the computer rooms because of my gender. And then when I went to university and undergrad and masters, coding was a thing for the male researchers. So it really was a great opportunity, and it has just opened up so many amazing research opportunities for me as well. And I try to coax students in from the world of field measurements and lab studies to the world of modeling. I'm not succeeding as much as I would like to, but it is truly an exciting place to be because there's a lot happening and a lot of really great communities to work with. The GeoSchem community is just a stellar example of an inclusive and welcoming and diverse environment. Of course, there's many people to thank at UCL, and I start with my thanks in case I run out of time at the end. Geography, Richard, as well, for propagating my work to the media, but also for organizing the inaugural lecture, for the support staff who handled all of my ignorant questions about how to put together a goddamn budget for funding. And then also beyond, Mark Gardner from Estates accompanies Eleanor every month up to the Max DOAS to make sure that it's running optimally. And then also people help me through the funding process and propagate my work to the media. It's been incredibly successful. Of course, faculty who provided support letters. There's an amazing cohort of people who were just so willing to step up and provide support letters towards my promotion. So I'm eternally grateful. Friends and family as well. I have some family online. And of course, as Danielle said, it won't take me 5 minutes until I mention that they're calling in from South Africa. And I stand between them and bedtime. So I will try to keep this light and entertaining. And then also networks and communities. I mentioned GeoSchem, and of course, Danielle has spoken about GeoSchem. It really is a special community. And I think it's a shining example that should be emulated everywhere else because it brings in these early career researchers with fresh ideas, with energy, and most importantly, time to contribute to the development of such a state of science model. And then also funders, those who have dared to fund me. I haven't said the opposite to those who haven't, but it has been important. It has helped me sustain a research group that has also gone on to do amazing research and who I've been able to train in these important skills. And of course, most importantly, to the members of this research group, I know that I'm probably not going to be able to represent all of the exciting research you do. It's no indication that I love your research less. I had to pick something to talk about within the limited time that I have, but you're what bring me into work each day that I come in, or each day that I get up and talk to you on Zoom and work remotely from home. You know, you keep me interested in the research. The fact that you are brave enough to look at all of these little exciting new projects really keeps me motivated to keep doing the research. And now on to that research. So I'm trying to link two aspects. Perhaps I won't be able to cover too much of the space sector component, but if I don't, you can ask Connor to talk to you a little bit more about this. He's really taken the charge in leading this aspect of the research. I might spend a little bit more on the agricultural sector. What unites these two sources of important pollution is that they are largely unregulated. On a global scale, there isn't really a shining example of a country or a region that has well-regulated agricultural emissions. We have some suggestions in the UK. Farmers are given documents that show them what sort of practices they could implement, but nothing that really legally binds them to implementing those. So it really is there is an inefficacy in trying to control agricultural emissions. So this is a sector to look at not only from air pollution perspective, but also from a climate change perspective. So sort of potential for co-benefits. And of course, I want my research, and the members of my group want their research to make a difference in the world. And so I have this very optimistic view of how we take data that we get from a model, from observations and so on. It's a very crude attempt at a screenshot from, I think, an Emacs window or something like that, showing environmental data. We work with much larger data sources. We take our expert analysis, we interpret it, we understand it, we might perhaps draw more inferences from it. It then undergoes peer review, we publish it, it undergoes the scrutiny of our peers, we then present it to our stakeholders, and voila, it's integrated in policy. We can write a NERC impact case and bring in a lot of money for the university, and we move on. But of course, we know that this doesn't happen. We have aspects like the data is not quite fit for purpose. We have to screen for poor quality data, and we end up with 10% of what we started with. We have slow funding cycles, so the expert analysis we want to apply or the postdoc we want to hire has to wait until the year or year and a half before the funding is actually secured. And then overheads consume the majority of the budget. So a year's postdoc turns into 6 months, so we have to adjust what we can really get done and so on. Oh, the joyous peer review. We have desk rejection. We resubmit addressing all of these issues. We have one obstinate reviewer who just won't let go of this one aspect that they really want us to work on more. They provide unreasonable revision requests, and by then the postdoc has moved. So we can't meet their unreasonable request. Then we've presented to stakeholders, and we do this within my research group as well. We present to stakeholders, not so much at such a high stakes environment, perhaps at a meeting where there are data providers who are calculating emissions from sources. And we offend them because we show that our data shows very different results to theirs. They want much higher spatial resolutions than we can achieve with our data. They want postcode level, and we can give them 10-kilometer resolution. And they're just overall unhappy with the findings. They wanted desert tusk from the Sahara to show up as the biggest issue because that's what they get the most complaints from if they're a local council, for example. So all of these steps in the process substantially delay the ability to really see your environmental data become integrated in policy and make a difference to society. So perhaps I'm not going to show you how we've got to this magical point right at the end, but I'm going to show you how we're progressing towards that stage. But we do have some success stories to celebrate. There is regulation that has been put in place that has led to a substantial decline in precursor emissions of air pollutants. Here showing the National Atmospheric Emission Inventory for the UK. These are emissions calculations that are determined by collecting things like activity data, number of cows in a field, number of cars on a road, the types of cars on the road, the fuel they burn, and so on, and applying some sort of emission factors, the amount of a pollutant produced per kilogram of fuel burned, whatever the activity is. And we see for these that are concentrated down at the very bottom of the plot, we've seen really, really large gains. This started off perhaps in 1952 as the shock event that instigated this. So it's a long road towards reaching these levels where we're at actually levels of SO2 or sulfur dioxide that we can't detect with most of our regulatory instruments. But there's one pollutant that shows up here as not having the same level of success, and that's ammonia. I've hopefully just referred to it as ammonia throughout my slides, but you might see NH3 crop up every now and again. And this is really the thing that comes from agriculture, largely from agriculture. Agriculture is the largest global source of ammonia. There are some natural sources, but they pale in comparison to agriculture. The UK ammonia emissions that are shown on the left here show the contribution of the different kinds of sources. dominated by things like cattle, other livestock like poultry and pigs, and then also fertilizer application, and then a few other smaller contributions. And you can see some attempts that have been made to try and look at the kinds of practices that are contributing to that, with near equal contributions from livestock housing, manure application, fertilizer application, all collected from this bottom-up approach. And so what we want to be able to do is assess whether this bottom-up approach is reliable enough, not only from a regulatory perspective to see whether we're meeting our emissions targets that are set for ammonia by regulatory mechanisms, but also whether the kinds of emission estimates that are being calculated on a sort of spatially aggregated scale are representative of the truth. So we don't really have the perfect ground truth, but we do have observations that are telling us about the amount of ammonia that is in the atmosphere. Essentially, these satellites give us data products that are counting the amount of ammonia all the way from the surface of the Earth up to the instrument, with most of it really concentrated close to the surface of the Earth. So these sort of 10 to the 15 numbers are just saying that there are many, many molecules within that column of air. And so we can use an instrument that's in low Earth orbit, the EASI instrument. It's an infrared atmospheric sounding interferometer. It passes overhead in the morning every day, and it has a really wide swath. So it's giving us daily global coverage. So very, very frequent set of observations. We have the issue in the US that it can't see through clouds, sorry, in the UK, where we unfortunately have a substantial amount of clouds. And so we have to use a lot of data. So we use 2008 to 2018. These are multi-year averages, but it has the advantage where it's actually quite consistent with how the NAEI is gathered. The NAEI is climatology. It's representative of a representative year, rather than capturing, say, interannual variability in things like temperature, relative humidity, perhaps agricultural practices that would cause ammonia emissions to vary from year to year. Here I'm just showing 2 months. We've been able to get this to actually finer scales than the nadir or native resolution of the instrument, because we use a gridding technique called oversampling. And so we've got these sort of 10-kilometer resolutions with the usual pushback that really what people want is at the farm scale. We can't deliver that. This is the best that we can do, and it's better than has been done before. Focusing on April and July, because these are 2 peak months that show up in the satellite record. April is when there is, well, March and April is when there's fertilizer application. It starts to warm a little bit, ammonia is volatile, and so more is released in April. And then July is the summertime peak that fascinatingly shows up in the satellite record, but we don't have it in our bottom-up inventories. We're not reproducing this with the information that we have from the bottom-up. We can use a very simple mass balance approach to say, well, we have these observations of concentrations of ammonia. We can run a model. We've heard this model mentioned many times now, GeoSchem, and the model gives us a conversion factor. What's the relationship between the column of ammonia in the air and the surface emissions? And we use that conversion factor to essentially convert the column concentrations or column densities into surface emissions. Very, very simple. There are far more sophisticated approaches out there, but this works relatively well for ammonia because it's quite short-lived, which means its location of enhancements in the atmosphere will be quite close to where it is emitted. And so we do this, and again, just focusing on these 2 months that stand out as the most interesting in terms of agricultural emissions, we get satellite-derived estimates shown on the left for April and July. The values inside the panels are just giving the totals for that month, gigatons or kilotons. I'm sorry, gigograms or kilotons. The middle is the inventory, the bottom-up approach, showing that in April, actually, if we compare the two, the inventory minus the satellite-derived values, they're consistent enough within the areas associated with the observations and the inventory, but there are much greater differences showing up in July. The bottom-up inventory doesn't capture this July enhancement. And this has implications for counting the number of ammonia, the amount of ammonia that's emitted, and just delivering this to regulatory agencies that are essentially checking that we keep within the limits that have been imposed. Something else that intriguingly shows up is where the discrepancy is greatest, is where other studies have shown these locations are dominated by dairy cattle farming. So it's directing further research toward looking at what might be causing these discrepancies, in particular in locations where the farming practices are dominated by dairy cattle farming. It hasn't really led to any directed studies yet that have helped to try and resolve this issue, but certainly there's awareness of this study as demonstrating a discrepancy between the two. And of course, I mentioned these stakeholder meetings. We've had meetings with UK DEFRA and with people in Europe, mainland Europe, who are also collecting emission inventories. And of course, that pushback is unfortunately sustained. There was lots of disgust at the size of the inventory values that we're getting versus what the bottom up is telling us. And so I perhaps not really covered this more formally, but the reason that we care about ammonia is because it can be transported away from these rural emission sources. It can interact with other aerosols in the atmosphere and essentially contribute to this aerosol mass loading of fine particles that we then breathe in deep into our lungs, and they go on to have a range of adverse effects on our health, and the most severe leading to premature mortality. We can transport this ammonia far enough to be deposited to sensitive habitats. The Peak District and Lake District, where my husband and I like to go hiking, is inundated with this nitrogen pollution. And then, of course, ammonia just suspended in the atmosphere is also directly toxic to prevalent plants within the UK. And so there's this sort of misconception that because ammonia is produced from rural agriculture, it's a rural pollutant. And so we wanted to try and upend this by using a model like GeoSchem to show that really agriculture is a source of pollution in urban areas as vast and as extensive as London. We started with Leicester. This was a collaboration with the Leicester City and County Councils, where they asked us to look at, from, I suppose, a peer review perspective, we were told this in our peer review, an eclectic mix of pollutants or sources that didn't seem to make justifiable sense, except for the fact that Leicester City and County Council wanted us to focus on these because this is the sources of pollution they can consider controlling, the ones that people call in the most about complaints, and so on. So this was gathered really in collaboration with the people who are developing local policies. Ignore the breakdown of the bars. That's only really for the atmospheric chemistry nerds who want to look at those specific bars. Focus really on the bold values above each bar, which are representing the quantification of the PM 2.5 that's coming from these individual sources determined from sensitivity simulations with the model. And what stands out, especially from a local council regulatory perspective, is that the city values, the local values, are far lower than any of the other sources that we looked at. And this has implications, which means that the local city council doesn't have much power to regulate local sources to be able to affect local air quality. It has to be a regional or county level regulation that needs to be put in place to have an effect on PM 2.5 in the urban environment, in particular agriculture, shows up as the largest contributor to PM 2.5. And of course, you know, some pushback that we would get is that, well, Leicester is a relatively small city. It is surrounded entirely by agriculture. And so what we did is also, I'm going to skip this little animation here, is that we extended this to look at much larger UK cities, Birmingham, and then anomalously large for the UK, London. And you can see their surface areas are vastly different. Leicester is quite representative of an average UK city. And so with looking at Birmingham and London, doing the same kinds of sensitivity simulations with the model, again, the UK agriculture source is almost exclusively dominant, except for the fact that London is very close to continental Europe and so does see influence from pollution transported from Europe, in particular in the springtime and wintertime. So this is a widespread issue covering all, at least, cities in England, where rural agriculture is having a substantial impact on PM 2.5 pollution, one of the most deadly air pollutants that exists. And of course, this this is not the satisfying finding that a local local city council wants, because they want to be able to regulate it away. And so again, it does require this, this really regional cooperation in order to improve air quality in urban areas. We extended this further to see, with the kind of regulation that is in place and the kind of technologies that are in place that exist for emission controls, what can we achieve not only in improving public health, but also ecosystem health across the UK. These bars are showing, I'll take you through them, estimates of emissions for the UK for 3 different pollutants I'm showing here, highlighting ammonia again as our key culprit, where these emission estimates come from an institute that essentially has the expertise to be able to calculate these, ingesting information about regulation and best available technologies and the influence this would have on future emissions of air pollution precursors. The acronyms here, PD is just present day, choosing 2019, steering far from 2020, where COVID did cause a bit of a disruption to air pollution sources. CLE is current legislation by 2030, and MTF is just indicating all readily available, technically feasible emission control technologies being adopted across all sectors. And so what stands out is for the sulfur dioxide and nitrogen oxides, all of these scenarios lead to decreases. Technology does far better if we were to force adoption of that. Ammonia, unfortunately, under current legislation is set to increase slightly. And this is as a result of just not having regulation in place. We've sort of regulated what we can with ammonia, like vehicle sources of ammonia, and perhaps food, demand for food increases. So this is all contributing to a slight increase. And then with maximum technically feasible emission controls, we can get down to about 20%. And so we can run with GSChem these emissions, which are gridded and also at fine temporal resolution, to be able to say what the implication is of air quality and also deposition of nitrogen to sensitive habitats with these 3 different scenarios, present day, and then our 2 future scenarios. So these are health calculations that Kern Bora calculated. He's the health expert within the group. And what we found was that for 2019, these are at municipal levels or administrative levels, the total premature mortality of people 14 years and older amounts to about 71,000 across the UK. This is actually a larger estimate than previous values, because this incorporates the most contemporary health risk assessment models. With current legislation, we can decrease this by about 13,000, and we can achieve double that if we adopt maximum technically feasible technologies. With accumulation of deposition of nitrogen, what this is indicating is essentially how much nitrogen is deposited above levels that are harmful to these habitats. I didn't bother showing the current legislation or the maximum technically feasible scenarios because it hardly changes. It doesn't move this 95% coverage of nitrogen above levels that are harmful much. I think it goes from 95 to 90%. So the current legislation, the maximum technically feasible controls that we have available have just about no benefits to ecosystem health. And so, of course, from this, what we find is that the data discrepancies that we get from our satellite-derived work warrants further investigation with a targeted focus on these dairy cattle farms in summer. We show that ammonia is not just a rural pollutant, that it is penetrating deep into very, very large and vast cities, and that there's health benefits that can be realized from both current legislation and best available technology. But we need far more aggressive controls to be able to affect ecosystem health. Some of the successes and sort of follow-ons from the study have been that we've been invited to give talks at stakeholder events with inventory developers as well as policymakers. We've been interviewed by NGOs and charities and other special interest groups, most notably the Soil Association, and just that discussion with the Soil Association sparked a new research project as well. We've had media interviews with a number of media outlets, some of them listed here, including long-form reports looking at legislation of agricultural sources. The paper on the satellite-derived emissions was also the most downloaded within its Wiley journal that we published in, a discipline-specific journal. And then also it led to me being invited as an ad hoc member of the UK Air Quality Experts Group, where I provided Earth observation expertise for a report on contemporary ways of measuring PM 2.5 within the UK. And so these are reports that are fed to DEFRA that can eventually lead to changes in how we monitor and regulate pollution. Has it altered regulation? Not yet. But perhaps based on the timescales that we've seen of the success of these emission controls, I'm being a little bit impatient. I'm expecting it to occur in sort of 2 to 3 years. But certainly there is momentum. There are discussions around ways that we could better monitor and regulate ammonia. I think because I'm very, very quickly running out of time. Oh, no, actually, I'm okay on time. I'll do, this is a bit of a lighter topic, less about premature mortality and more about things like rockets and re-entry space junk. So this is a project that was started by postdoc Robert Ryan within my group, also with a researcher who worked with me over the summer from University of Cambridge, who stayed in the lab world. I couldn't convince him to move over to the coding world. Put together an inventory of essentially air pollutant emissions coming from the modern space sector. And the reason why this is such an interesting area to look at is that there is this dramatic growth in space sector activity. On the left-hand side is the number of launches split into some of the dominant countries that are contributing to this. In 2021, the amount of launches occurring each year surpassed that of the first space race. And we're heading towards this 1 launch per day value. We're pretty close, probably about 2 or 3 or 4 years out. We're also seeing considerably more payloads, satellites being launched into low Earth orbit. And yes, I use satellite observations. They help me understand the atmosphere, but they're not the core contributor to this inundation of space junk in low Earth orbit. It really is Elon Musk and his lovely SpaceX darling. Also a South African, unfortunately. And so here we're getting pushback from industry in that they're counting the number of launches and they're seeing that they're far fewer and probably will never reach the levels of things like passenger flights. So no need to regulate. And there never will be a need to regulate because of the few launches that occur. And so what I'm trying to convince industry as well as regulators is that it's not about counting the frequency of launches in deciding what kind of impact the space sector will have on the environment. It's a unique pollution source. It's releasing pollutants into all layers of the atmosphere, not only from the launch process, but also from this atmospheric re-entry, the mechanism that's used to dispose of space junk. It enters through the atmosphere, it breaks up and ablates, and in that process produces compounds that are injected largely into the mesosphere, but also trickle down to the surface of the Earth. Whenever I'm interviewed by media about this, they first ask me about the carbon footprint, and I steer them very quickly away from that. CO2 emissions are not the things that we're most concerned about. Connor did a calculation on CO2 emissions for recent rocket launches, and it's the same as the CO2 emissions from the top 10 celebrities' private jets. So it puts it into perspective. It's important. They're releasing a lot of CO2 into the atmosphere, but it pales in comparison to all of the other industrial sources of CO2. And so because the chemicals are being released into much, much higher layers of the atmosphere, they stay there for much longer, 2.5, 3, 4 years, compared to pollution that's released closer to the surface of the Earth. At the surface of the Earth, we have weather. After a rainfall, it's essentially like the atmosphere taking a shower. It's clean, it's clear, and this process turns over by a few days. In particular for things like particles that are cleaned out of the atmosphere when it rains. Whereas in the upper layers of the atmosphere, we don't have this kind of weather. The main loss process is really slow gravitational settling to the surface of the Earth, which takes this sort of 2.5, 3 or more years, depending on a few properties associated with the atmosphere and the height that they're in and so on. And so this really warrants looking at this with something like a chemical transport model that reproduces these kinds of unique features. So in order to do this, we also needed to understand the kinds of pollutants that are coming from these rockets. we are not rocket scientists. This was a very steep learning curve for all of us involved in this project, but it's really exciting. There's a lot of energy around it. Elon Musk proposes these crazy outlandish ideas and everybody follows him. And so we start thinking about how these might affect the atmosphere. It largely depends on the type of fuel that's being used. And there are 4 key fuels, one that's starting to make inroads, a newer fuel. So solid, hypergolic, kerosene, and cryogenic are the 4 key kinds of propellants that are being used. Methane, liquid methane is a recent, is being used really recently. And so there's all these chemical formula names. I've included the description of them, but what they all produce is nitrogen oxides or NOx. They all also produce water vapor. 3 that are carbon-based also produce black carbon or soot particles. The solid rockets produce alumina particles and also chlorine compounds. The cryogenic is just producing NOx and water vapor. And so I've just highlighted the chemicals that are related to having a greater concern for climate because they're either absorbing or reflecting incoming radiation. And then the other chemicals that I've highlighted for ozone depletion. So they're depleting ozone, they're reactive, they're depleting ozone in the stratospheric layer that is protecting us from harmful UV radiation, potentially undermining progress that we've achieved with one of our most successful international environmental regulations, the Montreal Protocol. And so just putting that together for the climate effect and the ozone impact. But then I've also mentioned this re-entry process, and this re-entry process is a hot process. We have reusable objects. The SpaceX Starship first stage that's just been demonstrated to be reusable is producing NOx. You can see that flame that's being produced. It's hot, and it's hot enough to convert unreactive nitrogen in the atmosphere into reactive NOx. Similarly, discarded objects are going to produce this NOx via this high temperature process, but they're also composed of a whole lot of materials, some of which are metals producing metal oxides, and this provides a good surface for very fast ozone depletion to occur. And so what these are adding to is essentially this natural NOx and metal oxides that come traditionally from meteors. And so what we did at the time, this was, I think, 2020, when the most recent year that we had of space sector activity was 2019, is put together an inventory of these emissions, essentially calculating the timing and location and quantity of pollutants that are produced from all of the rocket launches that took place in 2019. Calculated the annual emissions and were able to then implement this into the GeoSchem model. In 2019, we only had 100 successful launches. We're now more than double that. And it also predates this era of satellite mega constellations. So for us, it was the modern space sector, but of course it's evolved considerably since we put together the study. We also incorporated space tourism. What could space tourism do if it really took off? It hasn't. So I don't know if we can thank ourselves for that. I think it's more incompetence by the people trying to lead those sorts of industries. And so what we did is, with this emission inventory, put it again into this GeoSchem chemical transport model that simulates atmospheric composition all the way from the surface of the Earth up to 80 kilometers. So getting a decent amount of this vertical profile of injection of pollutants. And what we can also do, or what already exists for GeoSchem, is this coupling to a radiative transfer model, which also allows us to assess the impact on climate by calculating a quantity radiative forcing, which essentially represents the imbalance in incoming and outgoing radiation. And so what we can do with this model is quantify the impact essentially as the difference in results obtained with the model with and without our rocket emissions. And so what we did is we also projected forward. We simulated it for 10 years, assuming a 6% increase in emissions per year, because that's what we had available. We had 2003 to 2019 growth rates. Of course, that 6% per year has been undermined by the current rapid surge in emissions. That's probably closer to 50 to 60%. Connor will tell you the exact value. I don't remember it offhand. And so what we were able to do is evaluate the decline in stratospheric ozone resulting from this injection of pollutants into the higher layers of the atmosphere. And what we found is that there's really a key regional influence. So it's largely the Arctic upper layers of the stratosphere, about 40 to 50 kilometers, where we're seeing a substantial decline in ozone taking place. And what was key about this, in large part because we also have most of the space activity taking place in the northern hemisphere, hence the bigger impact. In the southern hemisphere, I think there was only, one launch from New Zealand, maybe two, in the year that we looked at. What we got from this is about a 0.15% decrease in ozone in springtime over this portion of the atmosphere. And by coincidence, from Rob's literature search, he identified that this region of the atmosphere is where we've been able to quantify a clear recovery that we can attribute to the controls that we've applied to earthbound ozone depleting substances. And so we calculated that this ozone depletion that we've got from geochem represents about 10% of a reversal of this upper stratospheric ozone recovery that we've attributed to the Montreal Protocol, essentially undermining, again, this really, really important and successful international environmental regulatory body or movement. We also looked at incoming and outgoing radiation, and Seb is in the audience, and he will probably remind us that this is not the ideal way to do it. But we were still learning the process of trying to understand what the space sector is doing to radiation, essentially to climate. And so what we were able to calculate was what is happening at the top of the atmosphere? What is the imbalance between incoming and outgoing radiation? And what we calculated is this number, this 4 milliwatts per meter squared. And so this number doesn't have meaning without providing context. And so what we did is compare it to the value that's been estimated so far from anthropogenic sources, appreciating that, of course, the region where the influence is occurring is different, but it was useful to give a little bit of context to these black carbon particles that stay around in the atmosphere so much longer from these rocket launches. And we said that the rockets are representing about 3% of the radiative forcing that's been calculated from earthbound sources, even though they're only releasing about 0.01% of those emissions. And so this really did undermine the current sort of industrial pushback of the number of launches doesn't equal the number of aircraft, passenger flights, and so it'll never be a problem because it's a much, much larger issue. The black carbon coming from rockets has a far greater impact than the black carbon coming from these earthbound sources. So growth doesn't have to match that of passenger flights. And so just to conclude this section, what we did is assess the impact to be far more complex than just counting the number of launches or the number of re-entering objects. We identified that this black carbon or soot particles from rockets induce a far greater radiative imbalance than earthbound sources, and that ozone depletion is undermining the success of the Montreal Protocol. Sure, it's isolated in time and location, but it was important to highlight this. And unfortunately, the timing was not ideal because our study results are very modest in comparison to the very recent growth that's occurred in number of launches and number of re-entering objects. The rapid growth has occurred since 2020 as a result of the onset of this mega constellation era. We projected 3 more launches per year. What's really happening is about 40 launches per year. And so what's led from this is, of course, a swell of media attention when you say that space tourism has the potential to undermine the Montreal Protocol. Turns out media listen. And so we've had interviews and our research has been propagated by BBC, by The Guardian. I had a Sky News interview, unfortunately, while I was doing awful commute to and from Leicester. So I don't think I particularly looked my best on the one opportunity I was on live news, but so be it. Also media interviews and podcasts, one alongside Tim Peake. And then also, it was the most downloaded Wiley Earth Science, Earth's Future article in 2023. And of course, there's follow-on studies. So Connor Barker has taken this and improved it substantially, far better representation of the emissions coming from these sources, more complete and holistic representation of what's happening in the atmosphere by seamlessly updating the geochem model. But I think we're still in this position where it's challenging to convince industry to really support regulating the space sector activities beyond industries that are looking for good press with sustainability measures, but they're not the industries making the biggest impact. So again, we're not quite there yet, but you know, we're hopefully getting closer. This is certainly an area of research that we've had far more researchers getting on board with the same kind of models that we use and develop. So we're starting to build this body of evidence from very different models that represent the atmosphere in different ways, coming to very similar conclusions. This wealth of body of evidence. And so I just want to conclude with what I think might be on the horizon for research that I might pursue into the future, short of giving away all my ideas. And so really continuing to explore the future growth in the space sector. We are one of very few groups in the world who are looking at this. And so it has become somewhat of a niche for us. Doesn't mean that I've been more successful at applying for grants from this, but it is what it is. We're going to also incorporate recent observations that are being made as well as space sector pollution. We didn't have any way to constrain our model or evaluate our model with independent observations, and those are starting to become available. And I think what's going to keep air quality researchers like me and the people I train in business for a very, very long time is myopic sustainability policies and initiatives. And I've just listed a few here. I'm sure you could add to this list. So some that have been put into place or under consideration is something like cleaning up low Earth orbit by essentially increasing the number of re-entering objects, inundating the atmosphere with more and more exotic pollutants from satellites and other objects that we really don't have a handle on. We don't know their complete composition. These so-called carbon neutral rocket propellants that are also being derived with biomass that are certainly not pollution neutral. And then also this consideration of things like ammonia as a promising carbon neutral fuel. And ammonia oxidation, unfortunately, produces pollutants over the open ocean. This can lead to the production of NOx that can then spur the production of tropospheric ozone, an important greenhouse gas. So there's lots to explore on what the consequences will be to air quality and atmospheric composition as a result of that kind of measure. And then it's almost alarming to say this, that the UK plans to ramp up its refuse burning, domestic and commercial waste, to essentially generate energy. And the kinds of compounds that are buried within domestic and commercial waste can lead to the release of really toxic chemicals, carcinogens, and so on, but also reactive compounds that alter the composition of the atmosphere. So I think there's a lot that needs to be done, and there's an urgency to do it because these net zero and carbon neutrality ideas are being put into practice. So with that, I'll conclude, and I think if there's time, take questions, or we do the appreciation by Matt. You've been at UCL longer, you know the format.
I mean, there's no rules.
Okay.
You're inaugural, so let's do questions. There's always time for questions.
Okay. Yeah.
You have a large source of PM from anthropogenic dust.
Yes.
What is it?
I should have acknowledged that, riddled with uncertainty. So this is using the anthropogenic dust emissions that are calculated in geoschem. So they're not coming from the National Atmospheric Emission Inventory. And yes, when we presented this to policymakers, we threw in that huge caveat. Those are incredibly uncertain, and unfortunately uncertain in the wrong direction. They lead to very, very large PM 2.5, but we've just told them, ignore this. This is not something to go at in terms of regulation. That's all in the emissions.
Structure from road dust?
Oh, in reality, yes, yeah. But I think in the emission inventory, it's considerably exaggerated. There are lots that are available, which is, you know, on the UK Gov website, there are all these recommendations on best practices that would reduce ammonia. One is how the fertilizer is applied rather than sort of just spraying it out into the open air. You can, I think, apply it by burying it. Not a farmer, so I apologize for my poor terminology. And that reduces the amount of ammonia that's released. You can cover sludge animal waste, so that it doesn't release the ammonia either. There's many practices that can be put into place, but someone needs to push for it to happen, and there also needs to be support for farmers to implement these kinds of practices. Yeah.
The IADC, the Interagency Space Debris Coordination Committee, they recommend that everybody who puts a satellite into the orbit the satellite at the end of life should be deorbited within 25 years. And the current proposed mechanism is atmospheric re-entry and burn up and everything. What would the best replacement be?
Instead of that,
Yes.
no, it's actually decreased to 5 years. So it's gone from they've changed that the cadence will increase in terms of re-entry. So 25 years is even being pushed down to 5 years. You know, ESA is exploring options. NASA to a less extent. I think they're seeing ESA do more work and are trying to catch up. They're proposing things like having in-orbit repair of satellites that could continue to operate. But then you also have to consider how those new satellites are being put up there. You know, is that contributing now to a net increase in emissions because you have to get them there somehow? There's these sort of vacuum cleaner style approaches of essentially consuming them by, again, satellites that need to be launched. So ESA is exploring a few options, but I think all of them are not ideal. They're all going to produce chemicals in some way, and this is why these kinds of studies are needed, which is the least worst option to dispose of space junk, spent satellites, fairings, all of these components that get discarded. Yep.
Congratulations. First of all.
Thank you.
So the launches trend, I mean, it's alarming. I haven't come across that. So if it's, you said you had underestimated the projection was underestimating what would happen in the following years. So from what you understand, given that you've gone into this research quite a lot, is this going to be sustained? And in that case, I mean, is that going to be a big player in a variety of things in the future?
Yeah, it's a really uncertain sector. There are lots of reasonable and outlandish proposals of how we're going to use low Earth orbit, how we're going to mine asteroids. I don't know. There's so many crazy ideas that are being proposed that would lead to an increase in the number of launches. Connor, did you also add to that? Oh no, I think it was Lewis. Yeah. So, and the problem is it's so speculative. We can't really tell if this rapid growth that we're seeing over the past 3 to 4 years is going to be sustained, whether it's going to increase or not. It's exceptionally uncertain.
Meta have just announced that they want to do the same kind of Starlink thing, haven't they?
Oh yeah, there are many, many other companies that are joining this mega constellation, I don't know, idea. Yeah, not just Starlink. So we're going to see more of these launches of more satellites. We have rockets that are growing in size as well. Starship kind of knows how much bigger it is than the SpaceX Falcon 9, much bigger, burning far more propellant, releasing far more chemicals into the atmosphere. So even the number of launches doesn't quite tell us how much it's growing because it's also the propellant burn. It's $1 million question. I don't. But there's lots of spaces to watch, to see. There are so many wonderful space nerds who track this information online that we sort of piggyback on to keep track of what's happening in the space sector.
So ammonia, you showed this pretty worrying underestimate potentially in the emissions. What about other uncertainties? Could it be even worse than that if there are other uncertainties that are going to build on that uncertainty in the emissions or the underestimate?
You mean worse than we're estimating with the satellite-derived values?
Uncertainties in maybe the ammonia chemistry or in what happens afterwards.
You mean like the way that we're representing something like ammonia uptake to aerosols in geochem?
Right, so you showed this estimate of impacts. I'm kind of curious to know if you have to think that maybe even that's an underestimate beyond the underestimate on the emissions, but if you think that's closer to the truth.
I hope I'm answering your question, Zib. So we did, and I didn't say this about the GSK model. So we did, when we did these sort of impact assessments, we did update the GSChem emissions to better represent what the satellite-derived values are telling us. I hope that answers your question. Yeah, so addressing that bias before we run the model to calculate the impacts. But it's not an ideal addressment of that bias because there's a better mechanistic way that we could represent it, but we need those field measurements to tell us what's driving those emissions. Is it temperature? Is it relative humidity? Is it putting the cows out in the field, putting them in their housing?
You'll find in the UK repeated
It depends which findings. So certainly universally, there's no regulation targeting the agricultural sector that's leading to a decline in ammonia emissions. But the environments and the co-emitted pollutants are quite different in different parts of the world, the weather, the conditions, the kinds of farming practices, and so on. So I suppose China or India, as an example, they have far more of these other precursor aerosols that promote uptake to ammonia that make more PM2.5 than we see in the UK, but they're probably heading in the same direction as the UK because they have controls on those other co-emitted sources that are producing those pre-existing aerosols, those additional aerosols. So yes and no. The regulation issue is universal, but the kinds of chemicals that are in the atmosphere lead to slightly different amounts of PM2.5 being produced.
Building something like a direct air capture facility around, big emitting farms would help to find ammonia?
There are technologies that are placed on sort of large animal housings that capture those pollutants before they're released into the atmosphere, but no one is required to use them. So that's part of that sort of best available technology. It's there, it's ready, it's relatively inexpensive, it's technically feasible, but there's no push to adopt it.
Okay. So unless we have any other questions, I'd like to thank Eloise very much again for her lecture. Thank you. Very quick few words at the end of appreciation. I'd like to echo Danielle's comments and say, I know we're very lucky. And your loss is very much our gain. And it's a great pleasure to have Eloise here as a colleague, to be a member of the geography department and have someone who is doing such kind of vibrant and really interesting research. I'm kind of obviously interested from the perspective of remote sensing, but more generally these kind of big environmental questions and the questions that have the societal impact. And I can see your frustration of the difficulty of getting people to change their minds. But it needs this work, it needs this fundamental work, and it needs that somebody who's been prepared to put that in and to keep telling that story, and it's really interesting to see it. It's fascinating science questions, but it's how it's affecting people that's really important. And so it's great to have a colleague like that who's doing that and is really going to take this stuff forward, doing fascinating science, doing policy, doing outreach, doing education. So I think I would echo the feelings of many of us geography colleagues in the room, particularly, but UCL more generally, having to welcome somebody like Eloise as part of the professorial group here. But she's been doing great things for ages, and she's going to carry on doing great things. So thank you very much, and congratulations again.
Thank you.
I think Jan mentioned at the beginning, there's drinks and nibbles and so on outside, so please come along. And I was just waiting for the one last slide, which is all the good news about where the problems that we've solved.
Give me 20, 30 years.
Okay, no, come on, we need that now.